Welcome to this SC25 OpenMP Tech Talk. My name is Ruud van der Pas and I work in the Oracle Linux Engineering Organization. In this presentation, I would like to show you a tool called DTrace and how I use that to analyze an OpenMP application. After a brief motivation of why I'm interested in this work and why I think it's hopefully interesting to share, I want to talk a little bit about DTrace and cover some things that I'm going to need in the example. Because it's all about the example. It's an elaborate example. I did not want to be stuck with an hello world level kind of thing. I really want to show you how you can go pretty deep into an OpenMP application. And at the end, I'll have some wrap-up information like pointers to more information. DTrace is a dynamic tracing tool that traces activities in userland, the OS kernel, or both. And that makes it very interesting, because you can start looking at your application and then you go into the OS or you go into a library and you can see exactly what's going on. So it gives you that holistic view. The question I often get is, well, what's the difference with an application profiling tool? Well, an application profiling tool is excellent to tell you within the application what's going on down to the instruction level. That's not really what DTrace does. It gives you the big picture, but as you'll see, it helps us to find out what are the characteristics of our OpenMP application. And probably after that, you're going to grab your application profiling tool and zoom in on the kind of things that were exposed by DTrace. One of the nice things is that you get full control over what is traced and when. And that's a differentiator, because there are tools, and for example, I use strace, but strace, everything is fixed. I can make some choices, but I can't really have the control that I have with DTrace. And both, of course, have a right to exist. And I like the flexibility, but again, there are other tracing tools available. DTrace will give you that flexibility that other tools miss. And the way it works is you typically zoom in on an area of interest. You cast a fairly wide net, and then you go deeper and deeper to look at where your interest is. DTrace has been designed to be safe to use on a production system, and it's easy to use. It's all about the programmability of DTrace. You write your script or program, it's more like a program, but it's usually called a script, in a language called the D language. And don't worry, that's not an entirely new language. It has elements of awk, shell programming, and C. So if you're familiar with any of these, you'll find it really easy to use the D language. But you're in charge. And that's what I said. That's the difference between those other tracing commands, that you have some choices, but here you're totally in charge. And what I mean with that, you will see when I get to the example. And with that comes full flexibility, and you can also get really detailed information. For example, you can look into a function call, you can get a return value, you can get the arguments, you can see a lot. But you can also look at the OS scheduler. You can see what the scheduler does to your threads. And because you decide what to print and when, you have full control over the reporting. I'm now going to have a real short mini tutorial on DTrace. I just would like to show you some of the main things, and those are also the things that I'll be using in the example. DTrace is all about probes. A probe is nothing more or less than an event that you can trace. And every system where DTrace has been installed has a set of probes you can choose from. That's the set you're going to work with. You make your selection what you want to use. And an example is you can trace all the calls to malloc, for example. To make things a bit more manageable, probes are organized in sets they call providers, and you can get an overview of all the probes and all the providers on your system. You do that with the -L option on the DTrace command. But remember, you need to run DTrace with root permissions, because the kind of information it gets requires that. Run it under sudo. You can also run it as root, of course. The choice is yours. With that option, what we see, we get 5 columns. The first column is the ID. Every probe has a unique ID. Then the provider, and what I'm showing here, just a very small snippet of information. We see the provider is syscall, these are system calls. The module where they live in is VM Linux, and the function here is called getCWD, get current working directory. And we see on the name, we see entry and return. What does that mean? That means I can have a probe that will start working when I enter the function and when I'm about to leave the function. So you can look at the start and the finish, and that's a very useful thing. And that will come back again and again in the example. you make the selection what you want to monitor. So you have all your probes, you make your selections, and the wording is if the probe conditions are met, the probe will execute, you would say, but the terminology is fire. A probe will fire when the conditions are met. And when the probe fires, the constructs you use from the D language are executed. These actions are grouped in what's called a clause. That's one or more D statements. And just a technicality, a single probe may have more than one clause. Sometimes that's convenient. Or probes may share a clause, and that's actually what I have in the example I'll show you. Because very often the code you want to execute is almost probe independent, and it's a convenient way to group them together. This is the full definition of a DTrace probe. It has 4 fields: the provider, the module, the function, and the name, and you get that from the DTrace-L output we just saw an example. Then, for that probe, you define what needs to be done in case it fires, and that's called a clause. But sometimes you do not want the clause to be executed. There are good reasons why you don't want to do that, and that's one of the things I'd like to demonstrate in the example. And you do that by inserting a predicate. A predicate is like an if. It's a logical expression. If it evaluates to true, the clause is executed. If it evaluates to false, it's skipped. And in that way, you control the execution. And it's a very powerful mechanism, actually. And here's an example of a DTrace probe. I have 4 fields, as I was showing: syscall, VM Linux, getCW entry. That's a full name of a probe, but you can have wildcards. You can leave out a field, as shown at the bottom, where I have the syscall provider, but I don't specify VM Linux. I don't care where the function comes from. I'm interested in a function called write start. You can leave out fields, and you can also have wildcards within the names. So I want to look at every function that starts with write. That's what I'm saying there. And I want the probe to fire when I get into the return, so when I'm about to leave that function. With those wildcards, you can cast that wide net. And again, you'll see me using that in the example. Predicates, I just mentioned that, but they're important, very important in DTrace. You use it for control flow. The predicate is enclosed in forward slashes. There's a logical expression. If it evaluates to true or non-zero, then the clause will be executed. If it evaluates to 0 or false, the clause is skipped. And here's an example. I have a predicate, and I'm checking for the value of this variable var has been set. And what it means, if this variable has the value of 1, that means it's non-zero, then it's true and the clause will execute. If it happens to be 0, the clause will be ignored, skipped. And this is the equivalent formulation. It's a little bit longer, so it doesn't have to be 1 or 0. You can check for any value that you'd like to have it. You can use all sorts of comparisons. You can build up fairly complex logical expressions, but at the end of the day, they evaluate to either true or false. And this is a simple example of that. Aggregations are very important in DTrace. An aggregation reduces many data values into a compact aggregate like a single number. A set of numbers can be reduced to 1 by taking the minimum, for example. That's an example of an aggregation. DTrace has aggregation functions, and the results of those should go into a data structure called an aggregation. And an aggregation starts with the @ symbol. And here's the first example. My first aggregation, that is an aggregation because it's using the min function. That's an aggregation function, and it's taking the minimum of all the values that are passed in. The aggregation can be indexed. You can have an index. It's like an associative array. In this case, I have a key consisting of 2 fields, a string and an integer. And in that way, you can use aggregates in a more flexible way. And that's in the example. How to run your DTrace program. There are 2 ways. You can type it all in the command line. I would not recommend doing it, but the choice is yours. I prefer to store all my D commands in my probe definitions in a file and then execute that. So my focus is on the second method. The convention is, and you'll see me doing that, is you have the file end with .d. It's like an extension that immediately makes clear this is a DTrace script. You need to run DTrace with root privileges, so either directly as root or using sudo, and that's what I'm doing here, sudo DTrace. Then I need to tell DTrace it should take its program from the script. That's what the -s option does. And that brings us to the example. By now I have covered enough of DTrace to be able to show you what I'm doing there, and we're going to analyze an OpenMP application. I selected a graph analysis application being written in C, parallelized with OpenMP and compiled with the GCC compiler. That means that the OpenMP runtime library is called the GNU OpenMP library. It's libgomp.so, and that's what you'll be seeing me using as a module in my probes. Remember, the module was one of those fields, and I'm going to restrict all my tracing to whatever happens in libgomp.so. On the operational side, to keep the output manageable so I can put it on slides, I only use 2 threads, but whatever I'm showing you will run on any number of OpenMP threads. I picked a very short runtime. DTrace has very little overhead actually, but I just wanted to make my own life easier. Took a small example. On 2 threads, it took a little less than 4 seconds elapsed time and 7 seconds user time. And I wrote 2 DTrace scripts, and I did that on purpose to show you the methodology, because the first one will cast that wide net, and then I used that information to define the things that I'm really interested in. These are the 2 DTrace scripts that I used. The first one is called SC25-scan.d, and that's going to look at all the GOMP functions that are called and all the OpenMP runtime functions starting with OMP underscore. In that way, I see what happens sort of at runtime with those functions, and I'm heavily leveraging the wildcard feature here. Then that gives me the information to write the script that's going to do the detailed analysis for me. That's called SC25-OMP.d. And I'm going to zoom in and I'm going to show you thread statistics and timing. So there are 2 sides to that script. It will give you thread statistics, but also some timing information, because you can do both if you want to, and I wanted to do that. In both cases, I ran the program as under sudo. I will give it my script, and then I use the executable graph code, and I use the -c option on DTrace to tell DTrace this is the one that you should be probing. The first script, the very first part, the very first few lines. The first 3 lines, they customize the settings of DTrace. You can do that at the command line with command line options if you like. I prefer the pragma approach, so I don't have to worry about it anymore. At line 1, I silence the default output from DTrace, otherwise DTrace will give you some output, which is really useful in the development stage, don't get me wrong, but in this case I don't want to see that anymore. At lines 2 and 3, I tell DTrace to, when I print an aggregation, I want the output to be sorted by the first field in the key. First of all, by default, all aggregations are printed. You don't have to print them. When the tracing completes, all aggregations are printed. Again, very useful when you develop your script. But I want to have control over the printing, so I'm not going to rely on that. The default sorting is by the value. I don't want that. I want to have it sorted by the first column, so I pick my column with a specific purpose. And that's what we see here in these probes. There are multiple probes. They're defined at line 5 and 6, and since I'm using wildcards, at runtime they expand potentially to more than 2 probes. So let's look at it. At line 5, I use a provider called the PIT provider. I'll be brief on it. What it does, it will restrict the tracing to my target, my graph analysis code in this case. Only for that one I'll see the information. Then I want to restrict the information to anything related to libgomp. And then in blue we see gomp star. That means that every function starting with gomp should be probed, and I want to probe it on entry. So as soon as I enter one of those functions, my probe should fire. And here I'm using the same clause for all my probes, because at line 6 I have another probe definition, and that will look at all runtime OMP underscore functions. So that's a fairly wide net that I'm casting, and when that probe fires, I want to populate 2 aggregations. At line 8, calls underscore total, I use probefunc as a key. Probefunc is the name of the function, so that's one of those GOMP functions or an OMP function. And what it does, it's counting. Count is an aggregation function that increments each time the probe fires. So what I'm doing here is I'm counting how often these functions were executed. And I do that in 2 ways. At line 9, I add in the key, I add a thing called TID, thread ID. That's the DTrace generated thread ID. So for each thread in my application, I get a different count. In this way, at line 9, I differentiate according to the thread ID as well. So I get a global picture by looking at all the functions, and then I zoom in by looking at the distribution according to thread ID. And this is all that you need to do. Those 10 lines are literally all that I need to do to get that information. But I want to, as I mentioned, I want to have nice layout, and the end probe is a probe that's always available, and it only fires once after the tracing has completed. And my approach is that's when I print results, typically. But you don't have to do that, by the way. You can print results anywhere in the probe, whenever you want it. But I like to collect the information and then print it all out in the end probe, and that's what I'm doing here. The printf statements are like the same format as in C, print headers of columns, and at line 14, for example, print A, I print an aggregation, and I use formatted prints so that I can get a nice layout. I want to call out the second field there at line 14, %7 at D. Normally you would expect like %7D. The at symbol means that I'm going to print the value of the aggregation, in this case the count. And similar for lines 15 and 16. And with that, I get the following information for my test case. We immediately see there are 5 functions called, 3 from the GOMP library, internal library, and 2 from the OpenMP runtime library, and we see the call counts. And that's really, like I just said, just a few lines of DTrace and you get those call counts. But I also want to differentiate according to thread ID. That was my second aggregation, and that's what's shown here. And what we see here is I color-coded the one thread yellow and the other one is white. So what we see, the second thread calls 4 functions. The first one calls them as well, but it has one extra function. It's calling, it's highlighted in orange, GOMP parallel. That's the parallel region executed by the main thread. And we see the call count. So we see that we have almost 200 invocations of the parallel region. We also see we have 2,000 invocations of the barrier in both threads, and so forth. We also see that getNum threads and getThreadNum execute almost 200 times each. And just these few lines of DTrace will give me that information. These are the functions that I'm going to zoom in on, because I want to know more about them. And for that I wrote a second script, and that's shown here. The first 3 lines are the same. I'm setting my preferences. Then I have the first probe. It starts at line 5 and ends at line 12. The function that I want to look at is OMP getThreadNum. OMP ThreadNum will give me the thread ID. And I'm looking at the return. Why am I looking at the return? Well, I want to know the thread ID. I'm using this function to capture the OpenMP thread ID. And let's forget about line 6 for a few seconds and let's look at line 8. At line 8, I'm reading a variable arg1. Arg1 is a DTrace variable that gives you the return value of a function. In this case, that's the thread ID, the OpenMP thread ID. That's returned by this function. So what I'm doing at line 8, I'm storing that in a local variable, OMP_TID. I want to make that a clause local variable, so I use the keyword this. Didn't mention that, but that's the way to have like a local variable you would also have in other languages like C. So I get that variable, I get that number, so now I know the thread ID is stored in that value. Then at line 10, I fill my aggregation. I have an aggregation with 2 fields. The first field is the OpenMP thread ID. The second one is TID, that's the DTrace thread ID. So here I combine those 2, and I'm counting. But I know this probe will only be executed once, so this is a little bit overkill because of the following. So now let me go to line 6. Line 6 is a predicate. It checks for an associative array element indexed through the DTrace thread ID to be 0. Associative arrays are initialized to 0. What I'm saying here, if that array has not been initialized yet, in other words, it's the first time this probe fires, then you should execute that clause. Then at line 11, I change that value from 0 to 1. That means the next time, and the next time it will be skipped. So in this way, I make sure that this information is only collected once because I don't need it more than once. Then at line 9 is a little kind of thing that I want to use a flag. I want to use a flag for other probes to know that this OMP thread ID has been set, and that's what line 9 does. It's another associative array. Those are global arrays, so every probe can read them. And what it tells me, okay, you've set the thread ID for that DTrace ID. So that means that the operation was completed, and I can check for that later on, like in this probe. This is the second probe. And what I'm doing here, I'm looking here at OMP get num threads, again in the return part. And let's look for a moment at the result at 18 and 19. This is setting up another aggregation. And it has a key consisting of 4 fields. The function name, that's stored in internal variable probe func, that's OMP get num threads in this case. It's storing the thread count. Remember, this function returns how many threads there are, and return values are stored in arg1, so at line 17, I store that in a local variable. I could have just jammed in arg1 in this aggregation. I just want to show you how you can do this. It's a little bit cosmetic, but it also makes it a little bit easier to read because now you know what arg1 represents in this case, the thread count. The third field is the DTrace thread ID, and then the last field, THR map set. Well, what do I do there? That's set at lines 15 and 16. And what I'm doing there, remember on the previous slide, I set that associative array element, and I set it to 1 in case that probe fired. So this is like a flag. I use that as a flag. If the flag has been set, it means that I know the OpenMP thread ID and I can capture it. If the flag has not been set, it means that I did not execute the previous probe yet. I set it to -1. In that way, I have robust code. In case the OpenMP thread ID is not yet available, I'll see -1. Otherwise, I'll get the OpenMP thread ID. So this is how these things interplay. And that's why you need associative arrays and you need like aggregations. This sort of completed the thread part. I'm looking at some thread statistics. Now I'm going to look at timings. And for that I wrote another block of code. I have 3 probes here. Again, they share the same clause, which is very convenient. So I have the 3 probes. So I'm looking at those GOMP functions on entry. And on entry, line 25, whenever the probe fires, I'm going to just simply again do the counting, just as I did in my scanning example. I have the probe func. Probe func is an internal variable that will contain the name of the function, like a GOMP, whatever. Thread ID is the DTrace thread ID, and I'm just counting how often that is executed, how often the probe fires. Line 26 has a new element, the timestamp. Timestamp returns the absolute time since some moment in the past in nanoseconds. You typically use that to initialize a timer. So this is a timer variable, ts_start, timestamp_start. I index it through probe func because each function starts at a different time. So I need to differentiate according to the probe func, to the function name. I use a thread local variable. I don't have time to explain the ins and outs of that, but to be thread safe, I use the thread local variable. That's what the self with the arrow does. It declares this to be a thread local associative array element. That's at line 26. So here I'm setting things up. I'm counting and I'm getting the timestamp. Then in the next block of code, I look at the same functions, but now in the return. And what I'm doing there, first of all, I'm going to check at line 31, I have a predicate to make sure that the timer has been started. It should be, but it's good practice to be a little bit on the cautious side. At line 33, I now can calculate the time. I can take the timestamp again, and I subtract from that the timestamp that I got when I entered the function. This is a local variable, time. Time will give me, in a local variable, the time between the entry and the return. In other words, the time spent in that function. The value is given in nanoseconds. That's a very large number. So I divide by 1,000 and I get it in microseconds. This is a fairly long block of code, so it continues here. But now that I have the time, I can start storing information, and that's what I'm doing at lines 35 to 39. I have 5 different aggregations. They're all indexed by the probe func, the function name, and the thread ID, so I get the information on a thread basis. And what do I get? At line 35, I'm just summing up. Each time I get a new timing, I'm adding. So that will give me the total time for that function and that thread ID. 36 will give me a histogram. It will give me a time distribution. That's the quantize function. It will print you the time distribution, and we'll see that in the output shortly. So that's actually expanding to a whole sort of chart. Then I'm taking the minimum time, the maximum time, and the standard deviation, because I want to get a bit of feel for the spread in my timing. Line 41 is a technicality. Thread local storage is preserved, but I don't need that anymore, so I release that timing value, that starting value, because I'm done. The next time I go through the entry of the probe, it will be reinitialized. So in this way, I'm a little bit more memory conscious. Then there's a long end probe. When you look back at the code, you'll see that half of the code is spent on the probes, the core part, and the other half is spent on printing them, but there's nothing new compared to the other code you've seen. I'm just printing those aggregations, and I use printf to print headers, so I get nice tables with the information. And that even spans the next slide. But again, I'm not going to spend any time on it because I want to show you the results. And this is what we see. This is for the thread statistics part. And here we see the mapping. We see that a DTrace thread ID shown in yellow is actually OpenMP thread ID 0. And the other one is thread 1. And we know that probe only fired once, but the count confirms that was by design. I don't need to store that information again and again. I only need to have that mapping once. Then the second table, I was looking at OMP get num threads. That returns the total thread count. And what you see, the value is always 2. When you look at the count value on the last column, you see that those functions are called by each thread 198 times. And 198 times, I get the value of 2. In the OMP TID column, the second one from the right, you see values 0, -1, 1, -1. What does that mean? Well, that means that in 197 times I got the thread ID when I call that function. Remember, I spent some time to explain that I can't know when I get into get num threads that I already have the mapping. And what you see here, that situation happened once. So get num threads was called before I could set up the OpenMP thread IDs. Technicality, I could leave that out and you wouldn't even see it. But I want to illustrate how you can play with that information, how you can control what you're going to see and what's going to happen. But the bottom line here is that I'm calling OMP get num threads about 200 times per thread, and 200 times I get the same result. That seems like a bit of overkill. We're now going to look at the timing part of these probes. Remember, we wrote some probes for the timings. Well, this is the summary of the results. What we see our 5 comp functions, the thread ID of the thread that executed it, the count that we've seen before, but it's nice to have it all in one table, I think, and then the total time spent plus the minimum, maximum, and standard deviation. The first thing that we see the barrier. We see that the first thread spends way less time in the barrier than the second one. That's not a good situation. That should be equal. You don't want to have one really dominating the performance, and clearly the second thread spends a lot of time waiting, and that doesn't sound good. The parallel region is impacted by that because these barriers are in the parallel regions. There's no surprise there, but what we also see that the maximum time for the parallel region is very high. It's all sort of skewed by those long barrier times. The part that is okay is the single region. Both threads spend about an equal amount of time in it. There's not much variation, the spread is very low. For the single part we don't have to worry about that. But let's look at the parallel region, and in particular then the barriers in those parallel regions. The histograms. That was that quantize function I was talking about earlier. So for each thread I get this, and what you see a distribution. The value, that's the time in microseconds, and it's a bucket notation. So it's from 256 to 511, then 512 to 1023, and so forth. And what we see quite some timings in the lower ranges, but we also see, and those are color-coded orange, we see some really expensive long times in the parallel region. Only once, but they really skew the total performance. So those are the ones to pay attention to. We see in the barrier, now we see the differentiation of the times. We know that in the total there's quite a difference, but this is the breakdown over the barriers. And I think this is really valuable because what we see, the first barrier executed by the main thread has one outlier at the bottom. The rest is pretty quick. But now look at the other one, the other thread. It has many very short barriers, but when you look at the bottom, 61 times, the time is relatively high. And that barrier, that's the one that's causing a load imbalance because that's way more time. And now we know the details. We already knew that from the grand totals, but now we zoom in on the detail. The single region was very well behaved. We hardly spent any time there. And that's reflected in the distribution. It's very, very uniform and very little time. That's not a cause of concern. To summarize what we found, we had our two scripts, and collectively what we found was there were a lot of calls to OMP get num threads, about 200 times, but no change in the outcome, always returning the same number, although not a big deal. Seems like a bit of a waste to have it, and probably that could be optimized. What's much more serious is a high barrier call count per parallel region invocation and outliers. Outliers in the barrier and therefore also in the parallel region. So something is not well balanced here at all. And that's totally impacting the performance. So this code has a serious load balancing issue. And that points at a potential for improvement. So one thing you could go dig deeper with DTrace, although with the information we now have, I think it's time to use an application profiling tool and to analyze what's really happening deep in the code, because that's not so easy to do with DTrace. This is when you want to use the next tool, the application profiling tool, and find out how about these barriers. We know it's a problem there. To wrap it all up, I hope you agree that you can get quite some insight in a pretty easy way, and it's also very quick. You can't see that here, but these jobs run very fast. The overhead of DTrace is very small. I don't need to change the executable. I don't need to recompile or relink. I just use the executable I've always been using. So I'm also measuring exactly what I'm running in my production environment. And with DTrace, I can get quite detailed runtime statistics, and that helps me to understand the OpenMP behavior of my application. And what I've shown you are just the start. There's much more you can do. That's future work, but just that you know, this is only the beginning, not the end. Before I go, I would like to thank the following persons. Jacob Jelinek at Red Hat, he helped me a lot with my libcomp questions. Then Eugene Lowe, Chris Van Hees, Nick Alcock, and Alan McGuire at Oracle for very fruitful discussions on DTrace. Without these people, the presentation could not have been made. And any errors still there, they're entirely mine. In case that you're interested in learning more about DTrace, there's some training videos. They're free of charge. So you just go on YouTube. And there's a playlist, the link is given here. Search for Oracle Linux DTrace and you'll find these 4 modules, about half an hour, 35 minutes each. And they really get you started with the DTrace, lots and lots of examples. If you want to have a reference guide, there's a DTrace user guide, it's also online. You can either check it online or use the PDF. And with that, I'm going to stop talking. I hope you found this useful. And remember, if somebody tells you OpenMP does not scale, correct that person and say bad OpenMP does not scale. Thank you for your time and good luck with all your OpenMP work.